Hello guys, so welcome back to our lectures. So in this short video, we're gonna explore the common emitter amplifier pros and cons based on the circuit configurations that we saw in the last two videos, basically, or three videos. Okay, first one is our input. Our input was approximately R pi based on the circuit. Again, if we change the circuit, our input might change, as we will see. And R pi is, from hundreds to few kilo ohms. Hundreds, few kilo ohms. It's low to moderate resistance or value. And that's bad. That's one of the disadvantages of common emitter. It has relatively, we can say, low resistance. So that's disadvantage. It's bad. Okay. Number two, RO. For example, our input, in the example that we solved, it was 2.5 kilo ohms, and our signal was 5 kilo ohms. The internal resistance. So we need always our input to be higher than our signal. It was even lower. RO now. RO, again, based on the circuit we solved, it might change in another circuit, but most of the time, it was RC, equal to RC, exactly equal to RC. And RC usually few kilo ohms. It's moderate to high value. And that's also bad. We need RO to be small. In the example we solved, we need RO to be smaller than RL. In the example we solved it was 5 kilos and our load was 5 kilos. So half of the amplified voltage was wasted in RO. Number three, AV. Now let's talk about AV naught. So AV naught was minus beta RC over R pi. And if you guys remember, it was 200. So in the example, it was 200. It's basically hundreds, tens to hundreds. We can tens to hundreds, which is good. That's basically the most important advantage of common emitter amplifier. It usually have very high, amplification, very high amplification. That's really good. That's the basic advantage. Although the output is, has a phase shift with the input 180 degrees, or they are out of phase, as we said. But this is usually not a big problem. Okay. So here we have two observations, we can say. First, it's big, which is a good thing. Phase shift of 180 degrees. That's, not a problem. It's not advantage, but not a problem. Okay. Number four, high sensitivity. That's a big problem also in common emitter amplifiers. So basically, the problem is that beta is a function of temperature, a strong function of temperature. And this has two problems. The first one is, remember when we do the DC analysis, when we calculate IC is equal to beta IB. So if beta changes. So you bought a transistor with beta 100, you want it to be 100 all the time because you will do your calculations, you will do your design based on the assumption that beta is fixed equal to 100. But if you are in a warm place, it might be 120 because it increases because of the warm environment. Or it might reduce as well. This will move basically the Q point, and also it will increase or decrease or change or make the gain unstable, because look at the gain here. The gain is dependent on beta. If beta changes, increases, AV will increase. If beta decreases, AV will decrease. So this has two problems, not just one. So unstable Q point, DC Q point, I mean, because all our calculations in DC are based on beta. Number two, unstable gain. Why? Because AV naught is equal to minus beta RC over R pi. This is again for the circuit that we solved. Okay, that's basically, you know, the so here we see that the most advantageous, you know, point about common emitter is the gain, but we have a problem with our input, we have a problem with our output, we have a problem with the stability. But for the stability, we can solve it. Okay. So in the next video, we're gonna make a very little tweak in our common emitter amplifier circuit that we just solved in the last 3 videos. And we're gonna introduce a resistance, just one resistance, you know, one change. And this change will, you know, overcome some of these problems, either the instability in Q point or the instability in gain, or even low and high output resistances. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.